Hello my dear students, two chapters. The basic concept of these two chapters will help you a lot in solving the questions of mechanics in much easier way. I am telling about system of particles and rotational motion and work energy power. And in addition to that, one more chapter is there, that is gravitation. Yes, these are the three chapters for today's recap video. Welcome to another recap video of JEE Mantra 2025. So we are moving to the very first chapter here, that is work energy power, as I discussed. So here, first of all, we are going to tell about the work. Okay, so in this part, we will be discussing about that case where force acting is a constant and displacement is S, but there is an angle theta between force and the displacement. In that case, we will be calculating the work as F dot S or simply Fs cos theta. Alright, dot product between force and the displacement. And one more point is here that I want to discuss, that is SI system to CGS system conversion. If joule is the unit of work done in SI system, then erg is the unit in CGS system, and how they are connected, 1 joule equal to 10 to power 7 erg. That is the 2 points that I want to convey to you from this particular slide. Alright, moving to the next, that is about the dimensional formula. This already we have discussed in the very first chapter. Dimensional formula, this one is going to be ml square t raised to minus of 2. And here we are discussing a special case where, in which case we can have the work done by a force on a body to be 0. Possibility number 1, if displacement is 0. If displacement is 0, in that condition work done is going to be what? 0. And second case is that where theta is equal to what? 90 degree. That means force is acting on a body. I repeat, force is acting on a body, but still the work done by that force is 0. So which are the two cases possible, and which are that two cases where such a possibility can exist? Is first one is displacement in 0 and second one is theta. That means the angle between force and displacement is 90 degree. Okay, in the next slide we need to tell about work done by variable force. So here I told you force was constant and displacement was S, and there was a constant angle acting between F and S. Okay, there was a constant angle between F and S, and that was theta. But here the case is force is not a constant. Alright, in that condition what we do is we will consider any particular instant. Okay, and for that instant we assume that F vector is the force. Alright, and at that moment, because of that force acting on the body, let ds vector be the small displacement, very small displacement. So for that a small moment, the small work done is going to be what? F dot ds. Alright, and in order to calculate the total work done, we have to take the integral of that. Alright, so it's the total work done is going to be integral of F dot ds between the limit given. Alright, and this particular information is going to give you another very important information. Alright, and that is, if Fs graph is given, students listen carefully, if Fs graph is given, what is going to be the work done? So here it clearly throws the light to the concept that integral of F dot ds is what? The total work done. So if Fs graph is given, then area under the graph, I repeat, area under the graph with proper sign convention will help you in calculating the work done. Okay, so that was this particular slide telling you. And next one is this is now about the conservative as well as non-conservative force. Alright, so here I told you about the work done by a constant force and work done by a variable force. Now based on work done along a closed path, these forces can be classified into two. Okay, first one is conservative force and second one is non-conservative force. Now, what does it mean is, if you have a closed path like this, okay, started from A, it reached B, then C, D, and came back to A. So A, B, C, D, A. This is a closed path. So if a force is acting on a body, if one force is acting on a body and work done along a closed path is 0, then that particular force, I repeat, a force is acting on a body and it completed a closed path. Now, if the work done by that particular force is equal to 0, then the force acting on the body is treated as what? A conservative force. And as far as conservative force is considered, okay, the work done by that particular force never depend on the path followed, it only depend upon the initial and final position. All right, and if this condition is not being followed, then that particular force is known as what? Non-conservative force. So this particular part is telling about that, and they are giving few examples as well. Out of that, the first one is what? Gravitational force. All right, that means if I take a body from here to here, in this case the work done by the gravitation is what? Minus of mgh, because force is acting in the downward direction, displacement in the upward direction, theta is 180 degree, so the work done is going to be minus of mgh. And if I come back, then work done by gravitation there is going to be what? Plus mgh. Now the total work done is going to be what? 0. So one more example is given there, and example for non-conservative forces are also mentioned. The examples are friction force, viscous force, etc. All right. So the next I am going to tell you about the work done in case of compressing a spring. This is also an example of a variable force, because you all know that once I have a spring, something like this, okay, let me consider a spring at its natural length in this way, and if I press this spring through a distance of dx, okay, so not dx, let me press this through a distance of x. Okay, now at this particular moment, if an external agent is helping me, so of course this external agent need to apply a force of what? K into x to keep this body in equilibrium condition. And if we want to press this furthermore through a distance of dx, then in that condition I can say the small work done dw is going to be F, that's a force acting into displacement dx. So in that condition the small work done dw is going to be F was what? K into x into dx. And if I press this spring through a distance of capital X, now the total work done is going to be integral of this, and there I am going to get the value as half of K into capital X square, because I told you I am going to compress this through a distance of capital X. Here they took it as small letter x, that is the only difference. So I am taking it as capital X. So in that case, work done by the external agent, I repeat, work done by the external agent is going to be half of K into capital X square, and work done by the spring force, work done by the spring force, it's going to be minus of half of K into X square, and that much energy will be stored in the spring, and that is going to be termed as elastic potential energy of the spring. All right, fine. And second case, another case on the same page, that is they are telling a spring is having an initial elongation of x1, okay, and later on by adding some mass or by the help of an external agent, the extension changed from x1 to x2. Initially the extension is x1 and now it is being changed to x2. Okay, now just have a look. What is the final potential energy? Final potential energy is half of K into x2 square. That is the final potential energy. And what is the initial potential energy? Half of K into x1 square. I repeat, final potential energy is half of K into x2 square, and initial potential energy is half of K into x1 square. So the energy difference, definitely that is the by virtue of the work done by the external agent, isn't it? So the work done by the external agent need to be the difference of this. So basically it need to be half of K into x2 square minus x1 square. So that is going to be the additional energy stored in the spring. So that's mentioned over here. All right. And the last one is if a torque is acting on the body. If a torque is acting on the body, then how to calculate work done by that torque. Alright, because till now we were only discussing about force only. Now obviously the question will come, can only force do some work? Can a torque create some amount of energy or deliver some amount of energy to a particular system? Definitely the answer is yes. And if a torque is acting, that is tau, and the same way if it is creating an angular displacement of theta, there it was creating a linear displacement of s or ds, isn't it? For long displacement we took it as s, and for small displacement we took it as what? ds. Here a torque is acting and that torque is giving an angular displacement, and that angular displacement is given as what? Theta. In that condition, how to calculate the work done is, here the work done is going to be again the dot product between torque tau and angular displacement theta. Okay, it's there it was F dot S, here it is tau dot theta. That is the only difference. All right. So next we are going to the classification of energy here. So in this particular session we will be already discussing about the mechanical energy. Okay, like in this particular part we will be discussing about mechanical energy only. As you all know, we can have the classification of mechanical energy as two. First one is kinetic energy and second one is potential energy. Okay, kinetic energy is the energy possessed by the body by the virtue of its motion, and the mathematical expression for that is half of m into v square. All right, so kinetic energy we write it as what? Kinetic energy K, that is equal to half of m into v square. And here we can see one more relation. It's given as p square by 2m. Many a times the questions connecting these two were asked, like if linear momentum is doubled, what will happen to kinetic energy? Okay, if kinetic energy is halved, then what will happen to linear momentum? If kinetic energy is increased by x percentage, what is going to be the percentage change in linear momentum? So and so and so. So just because of that, you must know about the relation over here. It's very easy to understand because we all know that kinetic energy is what? Half of m into v square. All what you need to do over here is just multiply this expression with smaller term and divide by smaller term. Then on the numerator, it's going to be m into v the whole square. What it is? It's p square. So here comes the final expression. It is p square by 2m. So that particular relation is very, very, very important. And I told you how to fit that particular relation in your brain. All right. Next is potential energy. Potential energy is the energy stored in the given system by the virtue of change in position or the configuration. All right. So there itself, we must know what is going to be the relation between the force which is acting on the body, which is going to change the potential energy of the system. If the force acting is conservative, then definitely that is the one which is going to change the potential energy of the body. And if F is the force acting on the body, which is responsible for the change in potential energy of the system, then the relation between force and the potential energy is F is equal to minus of du by dx. I repeat, F is equal to minus of du by dx. Based on that, you can have two more relations like this. It's nothing, just rearranging the relation. Like for example, if I take dx towards the left, then it is going to be f dot dx is equal to what? Du. All right. And if I integrate this, integral of f dot dx between the limit x1 to x2, that will give the total potential energy. I mean change in total potential energy. This is du, that's a small change, and the integral of that one is going to be the change for the the total change. That means x1 to x2, if the force was acting, then what is going to be the total difference in the potential energy? That is going to, that uf minus ux will be giving you that particular value, and there that is going to be minus of integral of f dot dx between the limit x1 to x2 or xi to xf. Both makes the same sense only. All right. Now the next one is, I told you the potential energy. Okay, potential energy itself, we can have three classification here. Okay, so here this was the standard classification of mechanical energy, that is kinetic energy as well as potential energy. And here again we are discussing about what are the classification of potential energy. First one is gravitation potential energy, next one is elastic potential energy, and third one is electric potential energy. Gravitational potential energy is the potential energy stored in any given mass by the virtue of gravitational force. Okay, under the influence of gravitational force, if we change the position of any particular mass, then the energy gained by that particular body or the energy lost by that particular body, that is known as gravitational potential energy. This is very clear. It's by the virtue of gravitational force. And here next is elastic potential energy. This is by the virtue of the restoring force acting on the body, like the case of a spring that we can say. All right. And the last one is electrostatic potential energy, and that is by the virtue of electrostatic force of attraction or electrostatic force of repulsion between two charged masses. All right. So the basic expression that you already know. All right. Electrostatic potential energy, like if we are having two charges of charge Q1 and Q2, both are, I am taking, in this case I am taking both are positive only. So if Q1 as well as Q2 are the two charges which is kept at a distance of separation of small letter r, then electrostatic potential energy of that two charges is going to be 1 divided by 4 pi epsilon naught Q1 Q2 divided by r, where 1 divided by 4 pi epsilon naught is having the value 9 into 10 to power 9. All right. And the unit of that one is going to be Newton meter square upon Coulomb square. All right. And here one more information is there, that is the graph showing how the electrostatic potential energy, not electrostatic potential energy, here is going to tell you about, yes, potential energy versus x relation. Okay, fine. So here you can see this particular point here, x is 0. All right. So in this particular case we are taking it as r. So let me take here this as r. The distance of separation I am taking it as small letter r. Okay. So here when r is 0, in this particular situation, have a look. What will happen when r is 0? This electrostatic potential energy is going to be what? Infinite. Are you getting me? So we can never think that this particular relation is going to be represented by this particular graph. No. Here this is going to tell you only about the electrostatic potential energy of the spring. Okay, that means if the spring is having its natural length, okay, there we used to say that the extension of the spring is what? 0. At that time the potential energy is going to be 0. And if the spring is stretched, the potential energy will increase. And if the spring is compressed, there we are going to take it as negative. That's also going to compressed. Okay, so I can never say that this particular thing is for electrostatic potential energy. This graph is only for what? Only for elastic potential energy. Okay, and precisely I want to tell you the best example that I can immediately connect this particular graph is electrostatic potential energy stored in the case of a spring. All right, and how the potential energy of this particular thing is connected and how the relations are mentioned, we will be having a detailed discussion of this in that the very first chapter of +2, that is electric charge and electric potential. You can refer the detailed part over there. Okay, now next one is about the equilibrium condition. Okay, and this particular part is very important because graph related questions were asked many a times. All right, equilibrium type is of 3, that is stable equilibrium, unstable equilibrium as well as neutral equilibrium. I repeat, stable equilibrium, unstable equilibrium as well as neutral equilibrium. So stable equilibrium, the best example I can consider is a ball and a mass kept like this. Unstable equilibrium, the same horizontal surface but the ball is kept inverted and a mass is kept on the top. And neutral equilibrium is here. So I told you we are discussing about what? Equilibrium. The case of equilibrium. All right. So in that condition, since the case is of equilibrium, definitely the force acting on the body need to be what? 0. And we all know that F is equal to what? Minus of du by dr or du by dx. If force is acting along x axis, we will say it as du by dx, or generally we can say it as minus of du by dr. So since F is equal to 0, for all the case, minus of du by dr need to be what? 0. Minus of du by dr is going to be 0. Minus of du by dr is going to be 0. And here this is at stable equilibrium condition, potential energy is minimum, and if potential energy is minimum, then d square u by dr square, okay, that must be what? Positive. If second derivative need to be positive, and here potential energy is maximum, that means d square u by dr square, that need to be what? Negative. And here d square u by dr square, that need to be what? 0. So regarding equilibrium condition, these informations are very, very important, and the same thing is mentioned here as well. Okay, the next one is, yes, of course, the stable equilibrium and unstable equilibrium. So the entire information I have concluded in this single graph. All right, so for the detail, you can refer these particular portions also. Just pause the video and go through the the content over here. Detailed briefing is given. All right, so in short, this is the stuff. Detail, these two slides give the complete information in detail. All right, now let me take you to the next, that is work energy theorem. Work energy theorem says, if there are multiple forces acting on a body like F1, F2, F3, etc. Okay, let me limit up to 3 number of forces. So these 3 forces were acting on a body, and as a result of that, we observed a change in kinetic energy. All right, I repeat once again, 3 forces are acting on a body, F1, F2, F3, and as a result of that, we are observing a change in kinetic energy. Okay, then if I consider delta K as the change in kinetic energy of the system, then work done by force F1, let it be W1, work done by the force F2, let it be W2, and work done by the force F3, let it be W3. Then W1 plus W2 plus W3, that means the total work done by all the 3 forces is going to be equal to the change in kinetic energy. That is work energy theorem. That's simple. This information will help you in many cases, especially in those cases where you are going to have a problem where body is sliding from a top, and friction is acting. Okay, now there is going to be 2 work, isn't it? There is going to be 2 force, and as a result of that, there is going to be 2 separate work is being done by 2 separate force. One is work done due to gravitation, another one is work done due to friction. So the final kinetic energy or final speed, if they ask to calculate at the time of landing or once it reached the ground, what is the speed of the body? In that case, you can calculate simply the change in kinetic energy just by considering the work done due to the gravitational force plus work done due to the frictional force. Work done due to friction is going to be negative in that case. All right, in pure rolling that is not applicable, but in the case of sliding, work done is going to be what? Negative. All right, and work done due to gravitation is going to be positive. So work done by gravitation, that is positive, minus of work done by friction is going to be the change in kinetic energy of the body. All right, so that information will help you a lot. So exactly that thing is mentioned over here. And most important thing is this point number 2 here. Okay, this particular theorem is applicable to non-inertial frame also. Non-inertial frame means what? The frame in which law of inertia is not applicable. That means basically this, in short, whether the frame from which you are observing the system, it is accelerating or non-accelerating, work energy theorem is applicable on that. That means you can consider pseudo force also. In short, again making it short, what does it mean? You can consider the zero force also. All right. So that was this entire slide telling about. So work energy theorem. Total change in kinetic energy is the summation of work done by all the forces, and work energy theorem is applicable to non-inertial frame also. That is the entire slide want to convey you. Okay, the next one is principle of conservation of energy. You all know that what is principle of conservation of energy. Energy can neither be created nor be destroyed. If any energy change is happening, okay, if if you observe any change in value of any energy part, like kinetic energy is decreasing, potential energy is increasing, that means that particular part is getting converted from the given form to some another form. Okay, that means, for example, if we consider a system in which the mechanical energy is conserved, okay, if we consider a system in which the mechanical energy is conserved, mechanical energy, I already told you, we have got two parts for that, that is kinetic energy as well as potential energy. And once we say that the mechanical energy is conserved, that is the next point there on the slide. So once we say that the mechanical energy is conserved, that means the decreased value of kinetic energy is going to be increased value of potential energy, or increased value of potential energy is going to be decreased value of kinetic energy. Straight away I can give you one example. If I am going to have a body like this, a body which is coming with a speed of say v meter per second and the mass be m. So initially it's going to have a kinetic energy of what? Obviously half of mv square. And if I take ground as the reference, I can say that the potential energy here is going to be 0. Okay, potential energy, you always tell about the potential energy as difference in potential energy only. So here at this particular frame, I consider the initial potential energy as 0. Okay, now if this body is allowed to slide onto the top of this wedge, and I want to assume that this wedge is a smooth one, that means there is no frictional force, then definitely it will be going to climb up to a particular distance, and after that it will be coming back. Okay, so up to what distance it's going to climb is vertically, I can mark it as small letter h. So once it reach up to the maximum height, definitely you know that the speed of this body is going to be what? 0. So there the kinetic energy is 0. Okay, so the initial kinetic energy what it was having now got converted into potential energy. So for a moment it's going to be there at state of rest, and after that it will come back, and again it will be reaching here, and once it reach here, definitely the body is going to have the same old speed. So what happened? Kinetic energy converted to potential energy. It was there for a moment, it came back, and the kinetic energy again converted back to the potential energy. This is what law of conservation of energy, and this was specifically for mechanical energy. So kinetic energy got converted to potential, and potential energy got converted to kinetic energy back. So no energy part is being destroyed over there, they are getting exchanged from one form to another form. Okay, again this information is very important. Next one is power. The rate at which the work is being done, or the rate at which energy is delivered or energy is consumed. Okay, all the three cases we define that as what? The power. Power of dissipation, all right, power of delivery, or if we take a case of a machine, we are expecting some work to be done by that, then work done upon total time taken, that will give the power. Okay, so since power is work upon time, we all know that work is what? F dot ds. Work was F dot ds. So there you must know this relation. Power is going to be d by dt of F dot s. Okay, so here this is going to be what? F dot v, where v is velocity, because we know that ds by dt is what? Velocity. Okay, and there are few relations. Okay, so this was that mathematical relation that I just discussed over here. So if it is a dot product, you all know that that is going to be what? F into v into cos theta. Okay, now we have got few relations. What is the unit of power? Definitely you know that it is what? 1 kilowatt is 1000 watt, and here some another unit, horsepower. 1 horsepower is going to be 746 watt, and 1 kilowatt hour, this is not a unit of power. I repeat, this is not a unit of power, this is a unit of energy only. So 1 kilowatt hour, that is 3.6 into 10 to the power 6 joule. So this information is going to be very helpful. All right, but I repeat, this is not a unit of power, this is a unit for energy. Next, it's collision. Okay, once two bodies interact, it need not to be physical contact. It can be a case where two bodies are coming in contact by the virtue of contact or non-contact force. If the momentum or energy of the body is being exchanged. Okay, exchange means that it can be complete or it can be incomplete exchange. That particular phenomenon is known as what? Collision. Okay, here we are going to discuss basically in two categories, that was elastic collision and second one is inelastic collision. I repeat, elastic collision and second one is inelastic collision. Okay, in elastic collision, the kinetic energy before collision as well as linear momentum before collision is going to be same as that of kinetic energy after collision as well as linear momentum after the collision. In short, in case of elastic collision, kinetic energy as well as linear momentum both are conserved. I repeat, in case of elastic collision, kinetic energy and linear momentum both are conserved. But in case of inelastic collision, kinetic energy is not conserved. I repeat, kinetic energy is not conserved, but linear momentum is conserved. Okay, and in case of inelastic collision, there is one more category, that is perfectly inelastic collision. What it is? Perfectly inelastic collision. Why it is different in this case? Here also kinetic energy is not conserved, but linear momentum is conserved. But the difference is after the collision, the body will stick to each other. That means after collision, it is going to have a common velocity. That information is very important. In case of perfectly inelastic collision, after collision, the body will be having a common velocity, and that is what we mean to say that they stick to each other. So the classification is basically two, elastic and inelastic. In case of elastic collision, linear momentum is conserved and kinetic energy is conserved. In case of inelastic collision, kinetic energy is not conserved but linear momentum is conserved. And there itself we have got one more category, that is perfectly inelastic collision. Here also, as in the case of inelastic collision, kinetic energy is not conserved but linear momentum is conserved. But on top of that, there is one more specialty. After collision, the body will stick to each other. That means the final velocity of both the body is going to be the same. That means it's going to have a common velocity component. Okay, so that was the three category, and we need to tell about one more important term here once we are discussing about the collision, that is coefficient of restitution, or also known as coefficient of resilience. Coefficient of restitution or coefficient of resilience, basically it is velocity of separation. It is velocity of separation upon velocity of approach. I repeat, velocity of separation upon velocity of approach. So if there was mass m1 which was coming with a speed of u1, and there is another mass m2 that was going with a velocity of u2, and definitely u1 need to be greater than u2, then only collision will happen. So at a particular moment the collision took place, and after collision m1 mass is going with a speed of v1 and m2 mass that is going with a speed of v2. Okay, now v2 minus v1, this is what we call it as velocity of separation, and u1 minus u2, this is what we call it as velocity of approach, and this particular ratio is known as coefficient of restitution or coefficient of resilience. Okay, now for elastic collision, E is going to be 1. Okay, and for perfectly inelastic collision, I told you In case of perfectly inelastic collision, after collision they are going to have common velocity. So definitely v2 minus v1 is going to be 0. So in that condition you can see E is going to be 0. Okay. In case of inelastic collision, that was perfectly inelastic collision, and in case of inelastic collision, the value of E, that is going to be greater than 0, that is going to be greater than 0 and less than 1. I repeat, the value of E is going to be greater than 0 and less than 1, which means the maximum value of E is 1. So any case where E is given as 1.4, 3.2, 9.6, all those possibilities are never possible. Okay. So coefficient of restitution or coefficient of resilience, it is going to have the value of E maximum 1, that is for elastic collision, 0 for perfectly inelastic collision, and for inelastic collision the value of E is definitely going to be greater than 0 but less than 1. Okay. So that is what all that you must know regarding coefficient of restitution or coefficient of resilience. A few more things are there, definitely we will be discussing about that later on. And now in case of one dimensional head-on collision, so comes the question, what is one dimensional head-on collision? There the velocity of the two masses, okay, the velocity of two masses after collision and before collision, the direction is going to be along a same line. I repeat, like if I consider this case, u1, u2 were there, that was velocity component before collision, and v1, v2 were there, that was velocity component after collision. So these values u1, u2, v1, v2, they need to be in a same line. They need to be in a same line. Direction can be different. Direction can be different, that is not a problem, but that need to be in a same line. That means one dimensional. u1, u2, v1, v2, that need to be along a common direction. They all must be having common direction. It can be plus or minus, that doesn't matter. So all this should lie in a straight line or a common line. So that is the condition. So in that condition, after collision, particle 1 is going to have velocity as v1 as it's 1 here, so it's going to be m1 minus m2 into u1 plus 2 times, here it was 1, okay, here it is m2 u2 all divided by m1 plus m2, and for v2 1 will become 2 except this. Okay, so there it's going to be, v2 is going to be what, m2 minus m1 into u2 plus 2 times m1 u1 all divided by m1 plus m2. So this is going to be the final velocity v1 as well as v2 of these two bodies undergoing elastic collision. Okay, the values are familiar, like m1, m2, that is the mass of the body, u1, u2, that is the initial velocity, and definitely I told you this case is exclusively for elastic collision. All right, and now these are some important points regarding perfectly elastic one-dimensional collision. Okay, so I am going to repeat that expression for v1 as well as v2. What was v1? v1 was m1 minus m2 into u1 plus 2 times m2 u2 all divided by m1 plus m2. And what was v2? v2 was m2 minus m1 into u2 plus 2 times m1 u1 all divided by m1 plus m2. Now special case number 1. Special case number 1 is m1 is equal to m2. That means both the mass are the same. Okay, you just have a look. What is going to be the value of v1? If m1 is equal to m2, definitely this particular term is going to be 0. Okay, and m1 is equal to m2, and let me take m1 equal to m2 as small letter m. So this part is 0 now, and what I am having left over here is 2 times m2 u2 all divided by 2 times m, and here this is also what, m. I told you m1 equal to m2 equal to m. So 2m and 2m will cancel each other. So what is going to be v1? V1 is going to be u2. In the same way, if you solve, you are going to get v2 as u1. So basically, if mass is the same, I repeat, basically if mass is the same, then velocity exchange will happen. Okay, I repeat, velocity exchange will happen. Here I want to tell you something very, very important. A mass coming with a speed of 10 meter per second, say 2 kg mass, and it's going to collide with another mass over here that is also say 2 kg, and but this is at state of rest, 0 meter per second. If this collision happens, definitely what will be happening? This will come to state of rest and this will start moving. Okay, so that is a special case of what? Elastic collision. Okay, and another special case is, you consider m1 is very, very greater than m2. I repeat, m1 is very, very greater than m2. Thus this is special case number 2. m1 is very, very greater than m2 and u2 is equal to 0. m1 is very, very greater than m2 and u2 is equal to 0. Okay, in that condition what happens is, let us consider the case of v1. m1 is very, very greater than m2. So if m1 is very, very greater than m2, then m1 minus m2 is going to be what? m1 only. Okay, so that is going to be m1, and here this is what? u1, and u2 is 0, so definitely this is going to be 0, all divided by m1 is very, very greater than m2, so m1 plus m2 is also going to be what? m1 only. So this one and this one will cancel each other. That means v1 is going to be what? u1, which means the velocity of the first body is not going to change. Okay, not going to change. And what will happen to the second one? Have a look. v2. What is the expression for v2? v2 is m2 minus m1 into u2. So since I have got u2 as 0, so this entire term is going to be 0. And here this is what? 2 times m1 u1 all divided by m1 plus m2 is going to be what? m1 only. m1 and m1 will cancel each other. So v2 is going to travel with double the velocity of the first body. That means the heavier one, it will continue its motion with the same velocity, and the lighter body will be traveling with double the speed by which, precisely speaking, double the velocity by which the first body was hitting. That means we'll move in the same direction with double the speed of the heavier one. Okay, the third special case number 3, that is m2 is very, very greater than m1. m2 is very, very greater than m1, and again u2 is 0. Okay, so let's see what's going to be the value of v1. So this time m2 is very, very greater than m1. So if m2 is very, very greater than m1, this particular part is going to be what? Minus of m2u, minus of m2 u1. u2 is 0, this part will be 0 only, divided by m1 plus m2. m2 is very, very greater than m1, so m1 plus m2 is going to be m2, all divided by m2. m2 and m2 will cancel each other, which means here v1 is going to be minus of u1. That means the first velocity will go and hit the heavier one and will bounce back. Okay, that means it will bounce back with the same speed, but direction got reversed. That is what can see v1 is equal to minus of u1. And what about v2? What about v2? Have a look. m2 is very, very greater than m1. So this particular part is going to be 0 because u2 is 0. And here this is m2 u1 upon m1 plus m2. Isn't it? I repeat, 2 times m2 u1 upon m1 plus m2. Now the ratio m1 by m2 is very, 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 very less value. It's approximately equal to 0. So that means v2 is going to be what? 0. So the heavy body, it was at state of rest, it will continue at state of rest only. These special cases are very, very, very important. You must know it very well, and all happen just from these two mathematical expressions. So I just explained, you need not to memorize all these special cases. You must know these basic two standard expressions, and you must be able to come up with the final conclusion based upon the situations given. That was my only intent. Now moving to the next. So here, this particular expression, V1 as well as V2, I explained what is going to be the velocity of the body after collision, elastic collision. So in this case, this is inelastic collision. So coefficient of restitution is not 1 here. It is going to be a value greater than 0, less than 1. In that condition, what the value is going to be? V1 is, okay, see, have a look. It is M1 minus of E into M2 into U1 plus, here instead of 2 we are having 1 plus E into M2 U2 all divided by M1 plus M2. Okay, similarly V2 is going to be M2 minus E times M1 into U2 plus 1 plus E into M1 U1 all divided by M1 plus M2. The only difference is there it was M1 and M2, here E is appearing. Instead of 2, 1 plus E is coming. That is only, just substitute the value of E equal to 1, you will get the exact same expression. Alright, and one more thing regarding loss of kinetic energy. In case of inelastic collision, there it's going to be delta K equals to delta K, that is going to be equal to M1 M2 into U1 minus of U2 square into 1 minus of E square all divided by M1 plus M2. So that is going to be loss of kinetic energy. I think we're 1 by 2, yes, 1 by 2 must be there. Alright, okay, so this is going to be the loss of kinetic energy. Questions were very rare from this particular part, okay, but this information is again important, okay. And the next one is perfectly inelastic one-dimensional collision. I repeat, perfectly inelastic one-dimensional collision. You know that velocity of separation is 0 after perfectly inelastic collision. So in that case, the loss of kinetic energy, there it's going to be M1 M2 into U1 minus U2 the whole square all divided by 2 times M1 plus M2. That's going to be the loss of kinetic energy. Okay, and the next one is, this is very important. Okay, I can tell you how this need to be understood. Let a body is being dropped from a height, say h. So once it hit the ground, just before hitting, it's going to have a speed of v. Alright, let it be v0. Just before hitting the ground, the speed is v0. And if it is an elastic collision happening here, the body will go back to the same height. That means the velocity by which the body bounces back, it's also going to be the same. This is possible in the case of elastic collision. Isn't it? And if we are having a case where this is not elastic collision, okay, the body came from a height h and landing here with a speed of v0, and now is going back with a speed of v. Okay, now of course velocity of separation is v and velocity of approach is what? V naught, isn't it? So velocity of separation upon velocity of approach, that is what we call it as what? Coefficient of restitution, isn't it? Now if this came from a height of h, after collision it's going to reach up to a height of what? Let this be h0, and now it's going to reach up to height of what? H only. Now how to get this value? Definitely we know that v square, that's going to be what? 2 times g into h. And what is V square? V square is E square into V naught square. Okay, that is going to be 2 times G into H. Now let me take this 2G down. So E square into V naught square divided by 2 times G, that is equal to H. And what is this? This is H naught, isn't it? That means H is going to be E square. I repeat, H is going to be E square into H naught. Okay, this is after one collision. And after one more collision, this is going to be what? Again, the height is what? This time the height is height is H. So what was the previous height? That is H naught times E square is there. Now this time, after the second collision, the height is going to be, let me say H dash. That is going to be E square times H. And what was H? What was H? It was E square into H naught. Okay, it will keep on going like that. Okay, so now have a look. Now you will understand these relations. E is equal to V1 by V naught. Okay, velocity of separation upon velocity of approach. In terms of height, it is 2h1 upon 2h naught. Alright, while taking the ratio, it's going to be under root of h1 by h2. And how the height is varying? Just have a look. E raised to n, that means after the nth collision, is going to be Vn upon V naught. Okay, and here, after n rebounds, how the height is going to be? It's e raised to 2 times n. How? See here, after 2, it was e raised to 4. It's 2 times 2. Alright, so here, after n number of collisions, it's going to be e raised to 2 times n. After here, in that case, you can have a look. Here it was 2, so n became 2. And if it is 3, this n is going to be what? 3. And after fourth collision, n is going to be 4. Okay, so after n collision, this is the expression. I believe you got it. Okay, so this particular part is very, very important. The basic thing that you must know is this. Okay, how the velocity is changing. From there, you can easily come to the conclusion regarding the height. I hope it was perfectly alright with you guys. Okay, next one is two-dimensional or oblique collision. So here, have a look. This is mass m1, and that is coming here with a velocity of u1, and with respect to x-axis, it's making an angle alpha 1. And here you can see mass m2 that is approaching with an initial velocity of u2, and angle made is what? Alpha 2. So the collision happens, and after collision, m2 move away with a velocity of v2, making an angle beta 2, and m1 moving away with a velocity of v1, making an angle beta 1. Okay, now what you must understand is whether it is elastic, inelastic, or perfectly inelastic, linear momentum is conserved. And once I say linear momentum is conserved, okay, it need to be conserved along x-axis, it need to be conserved along y-axis. So you must understand this is happening along a plane, and for me this is x-axis and this is y-axis, and from the plane perpendicularly outward, that is z axis. Okay, so I have got 2 axes on the plane, that is x-axis as well as y-axis. We are looking from the top and we are able to see the x-axis as well as y-axis, and z-axis is pointing towards us. In that way you must understand. So the initial linear momentum along x-axis, dear, tell me what is the initial linear momentum along x-axis? For mass m1, it is having its initial linear momentum along x-axis as m1 u1 cos of alpha 1, plus for the second one, it is m2 u2 cos of alpha 2. That is initial linear momentum along x-axis. Final linear momentum along x-axis is going to be what? m1 v1 cos of beta 1 plus m2 v2 cos of beta 2. This must be the same. Okay. Similarly, you can take it for y-axis as well. I hope you got it right. Okay. And the same thing is considered here as well. They took the linear momentum along y-axis. That also need to be the same. Now we have got one special case. That is, if m1 is equal to m2. I repeat, if m1 is equal to m2 and alpha 1 plus alpha 2 is equal to 90 degree. That's a special case. Okay, you can mathematically prove this relation also. m1 equal to m2 equal to m and alpha 1 plus alpha 2 equal to 90 degree. In that condition, after collision, the summation of beta 1 plus beta 2, summation of beta 1 plus beta 2 also must be equal to 90 degree. That's also a very helpful information. All right, so that particular information will help you in many ways, so you must keep that in mind. That is, what was that? Repeat, if m1 equal to m2 equal to m and alpha 1 plus alpha 2 equal to 90 degree, then after collision, the final angles that makes with respect to x-axis, beta 1 plus beta 2 also should be equal to 90 degree. And here comes the another one. Here you can see m1 mass is traveling along x-axis with an initial velocity of u meter per second, and that is going to hit m2, and after hitting you can see m1 is moving with velocity v1 making an angle alpha, and m2 is moving with velocity v2 making an angle beta. Here also law of conservation of linear momentum is conserved along x-axis as well as y-axis. So initial linear momentum along x-axis. Initial linear momentum along x-axis is what? m1 into u1. Not u1, it's m1 into u. Okay, and final linear momentum after collision, that is final, isn't it? Along x-axis need to be what? It need to be m1 into v1 cos of alpha plus m2 into v2 cos of beta. Okay, that is for x-axis. And for y-axis, you know that there is no initial linear momentum along y-axis. So final linear momentum along y-axis also need to be what? 0. That means m1 v1 sine of alpha in the upward direction. So upward direction I am taking it as positive. Downward direction I am going to take it as negative. So minus of m2 v2 sine of beta need to be equal to what? 0, because initial linear momentum along y-axis was 0. Next is system of particles and rotational motion. Okay, fine. And what's special with this chapter is, this is really going to be a chapter that will help you to analyze your understanding towards the entire concept of mechanics that you have studied till now. Okay, so let's verify that. So the very first thing is about center of mass. It is that point on a body where the entire mass of the body is assumed to be concentrated, and if we want to study the motion of such a rigid body, okay, then what we can do is we can assume all the forces acting on that particular body to be concentrated onto that single point where the entire mass is concentrated, and later on the motion of that particular point will define the motion of that rigid body as a whole, especially the translational motion. Okay, so that is what center of mass is. So the textbook language is that point where the entire mass of the body is assumed to be concentrated. All right, and what is the benefit of that concentration for us? That is what I said was that, okay, it will help us to analyze the motion of the body. All right, so here regarding the center of mass, we are going to discuss about the position of center of mass. Okay, its its x coordinate, y coordinate and z coordinate. This relation will give the general expression, and here this gave the x coordinate, y coordinate as well as z coordinate of its center of mass. Now let us see what does it mean. Let us consider a system which contains n number of particles. Mass is m1, m2, m3 etc. up to mn, and the position vector of the mass is given as r1 vector, r2 vector etc. up to rn vector. Then the position of center of mass of the system is going to be m1 r1 vector plus m2 r2 vector etc. up to mn rn vector, all divided by m1 plus m2 etc. up to mn. And if we are provided with the x coordinate of these masses like x1, x2, x3 etc., then xcm, that is the x coordinate of the center of mass, is going to be m1 x1 plus m2 x2 etc. up to mn x1, all divided by m1 plus m2 plus m3. Similarly, you can calculate ycm as well as zcm. Okay, the next one is, if we are provided with two particle system like m1 and m2, they are kept at a linear distance of separation of small letter d. Okay, then the center of mass of this system with respect to m1, I repeat, with respect to m1, in that case what you have to do is, you have to take this particular point as the origin. Okay, now once I take position of m1 as the origin, so the position of m1 with respect to origin is going to be 0. So m1 x1, that term is going to be 0 here. m2 x2, x2 is d here, so it's going to be m2 into d divided by m1 plus m2. That is what you can see here. So this is from m1. Okay, this is not the position, that I just mean to say that this is from m1. So from m1 it is going to be at a distance of m2d divided by m1 plus m2. And if you want to take with respect to m2, then you have to take m2 as the origin. Now position of m2 with respect to origin is 0. Now it's going to be m1 into d divided by m1 plus m2. So that you can see here. Okay, and if r1 and r2, I repeat, if r1 vector and r2 vector is given as the corresponding position vectors, then it is going to be m1 r1 vector plus m2 into r2 vector, all divided by m1 plus m2. I hope you got it right. The next one is about the velocity as well as acceleration of center of mass. If m1 r1 plus m2 r2 divided by m1 plus m2, that was the position of center of mass, definitely the rate at which the position is going to change, that will give the value of velocity, and the rate at which the velocity is going to change with respect to time. Rate means with respect to time only. That is going to be what? Acceleration. So once we differentiate the expression for RCM, definitely we will get what? VCM equal to m1 v1 plus m2 v2 divided by m1 plus m2. And once we differentiate the expression of VCM with respect to time, then we will get what? ACM, that is equal to m1 a1 plus m2 a2 divided by m1 plus m2. So that are these two expressions here. This is for velocity of center of mass, and this one is for acceleration of center of mass. All right, next one is some important points. Okay, and out of that, the first one, the position of center of mass depends upon shape, size and mass distribution of body. Conceptually, these points are very important. Second one, the center of mass of an object need not to lie within the object, it can be outside the body also. Okay, the next one, in symmetrical bodies, I mean the case the body is having symmetrical mass distribution, the geometric center itself is going to be the center of mass. Okay, and the last one is the position of center of mass on object changes in translatory motion but remains unchanged in rotational motion. That is very, very, very important. In translation motion, the chances of the position of center of mass being changed is there, but in case of rotational motion, it's not there. Okay. Now, what about the linear momentum of the system? Okay, if m1 v1, m2 v2, m3 v3, etc. up to mn vn, these are the corresponding linear momentum of a particle that contains n number of masses with velocities v1, v2, v3, etc. up to vn. Then the summation of all these, okay, the summation of all these particles, linear momentum, okay, altogether will give what? The entire linear momentum of the system. Okay, and that is going to be what? The total mass of the system into velocity of center of mass. Okay, that's what this particular relation says. And the next one is, if an external force is acting, okay, the way we consider it for a single particle system, the same thing is applicable here. If F is the force acting, then that F external is going to be rate of change of linear momentum, and we take the linear momentum as this one here. Okay, that means total mass into velocity of center of mass. That's what we are going to discuss over here. And the next one is rotational dynamics. In rotational dynamics, we are going to discuss about the final velocity, angular acceleration, angular displacement of a body rotating with respect to a particular axis, okay, and that experience a constant angular acceleration. So before going in depth, we must know what you mean by a rotational motion. So rotational motion means the particle of the entire body, all the particle of the entire body will be moving in a circular path. All the particle will be moving in a circular path, and the center of all these circles is going to be the same. Okay, and that's going to lie in a common line. That's the center is going to be collinear. Fine. So that type of motion is known as what? Rotational motion. I repeat, that is known as what? Rotational motion. And in that rotational motion, if the angular velocity is changing at a constant rate, that means if the angular acceleration is constant, the way we have the equations of motion in translation motion, here also we have got equations of motion, and that is, there we have what? V equal to u plus at. Here we have got omega equal to omega root into alpha times t. There we have got s is equal to ut plus half at square. Here we have got omega naught into t plus half of alpha into t square. V square equal to u square plus 2s. Omega square is equal to omega naught square plus 2 times alpha into theta. Okay, here omega is the final angular speed or a final angular velocity, we can say. Omega naught is the initial angular velocity. Alpha is angular acceleration, and theta is the angular displacement, and of course t is the time taken. All right. The next one is moment of inertia. Basically, inertia of rotational motion is known as what? Moment of inertia. That means, what was the role of mass in translational motion? Here, the moment of inertia is going to play the same role. And if I have got a mass m, okay, which is moving in a circular path at a distance of small letter r from the axis of rotation, then the moment of inertia of that particle with respect to its axis of rotation is going to be m into r square. I repeat, m into r square. And if you have got a system where there is n number of particles, the total moment of inertia of the system is going to be m1 into r1 square plus m2 into r2 square, etc. up to mn into rn square. So that is these two relations saying. And of course, finally, the dimensional formula as well as the SI unit. Dimensional formula is capital M into L square, and the SI unit is kilogram meter square. Okay. The next one is, what all are the factors on which the moment of inertia of a system depends? Let's see. First one, the position of axis of rotation. Okay, with respect to which axis the body is rotating, definitely that matters. For the given body, its axis of rotation, it matters. Second one is the orientation of the axis of rotation. Okay, orientation, not only the axis of rotation, orientation also it matters. Next one is shape and size of the body, and after that distribution of mass about the axis of rotation. So these are the 4 points that determines the moment of inertia of a body rotating. All right, the next one is radius of gyration. I repeat, radius of gyration. So here radius of gyration means, see, we know if there is a particle, this is a system of particle that contains m1, m2, m3, etc. up to mn masses at a distance of r1, r2, r3, etc. up to rn. All right, then the mean square of these particles stands for the radius of gyration. Okay, so if you have got discrete mass distribution, I am saying discrete mass distribution, then the mean square of these particles, okay, that is going to be the radius of gyration if it is a discrete mass distribution. And if it is a continuous mass distribution, then if I is the moment of inertia of the system, then we have to write it as m into k square, where m is the total mass and k is going to be the radius of gyration. So here I upon capital M all root, that is going to be the radius of gyration. Okay, so you can see the same relation here. K is equal to I upon M. So this is for discrete mass distribution, and here this is for continuous mass distribution. All right, next one is parallel axis theorem, and the next one is perpendicular axis theorem. So here what parallel axis theorem says, if you want to find out the moment of inertia of any body with respect to an axis like this, okay, an arbitrary axis like this, you want to find out the moment of inertia of this particular body with respect to this axis. So how to find out that? Okay, so this theorem will help us in finding so. So let this axis be a dash, okay, and let the moment of inertia of this particular mass with respect to a dash be I. Now first I want to do is, I am going to find out the center of mass of this body, and let this be the center of mass. Okay, here this is the center of mass, and let this be an axis passing through the center of mass. Not only that, this need to be parallel to a dash. So b dash, it is an axis that passing through the center of mass and parallel to a dash as well. And the moment of inertia with respect to b dash, let this be ICOM, moment of inertia with respect to center of mass. And let the distance of separation between this is given as, say, small letter d. Here it is taken as small letter r, anyway it be small letter d in my case. So here the moment of inertia I, this was what we wanted to calculate, that is going to be moment of inertia with respect to center of mass plus mass of this body m into the perpendicular distance of separation between these two masses. This is what we call it as parallel axis theorem. Okay, next is perpendicular axis theorem. Here we have got a two-dimensional mass distribution. What? Two-dimensional mass distribution. And this, let this be the two-dimensional mass distribution. Okay, now let this be z-axis, let this be x-axis, and let this be y-axis. Now z-axis and x-axis, that lies in the plane of the mass distribution. Now moment of inertia of the system with respect to z-axis plus moment of inertia of the system with respect to x-axis. These two lies in the common plane. That is going to be moment of inertia of the system with respect to y-axis. This is parallel axis theorem. And something very, very important I want to tell you. And what it is, perpendicular axis theorem is not applicable in all cases. That is applicable only in case of two-dimensional mass distribution. But parallel axis theorem, that is applicable in all cases. That is very, very important. Ever, never forget that. Okay. Next one is the same thing only, the mathematical relation of this one. Next one is moment of inertia of some homogeneous rigid bodies. Out of that, the first one is circular ring. Okay, you need to be extra careful in this segment. So here this is a circular ring. So the moment of inertia is going to be what? mr square through its center of mass, because all the mass distribution is at equal distance. All mass distribution is at equal distance. So the moment of inertia is going to be mr square. Now this time I am shifting the axis from here towards the right. Now parallel axis theorem is going to help me. Who is going to help me? Parallel axis theorem is going to help me. What is the distance of separation between this? R. What was the moment of inertia with respect to this? It was mr square. So mr square plus mass of the body is m, perpendicular distance is r. So the new moment of inertia, it's going to be what? 2 times m into r square. See? Alright? Isn't it? Yes. Next one. About the tangent in the plane of the ring. Okay. So before going that, let's discuss this. What I am going to do is, this is the ring. We know the moment of inertia with respect to this axis. What it is? It is mr square. Now I am going to take two perpendicular axes in the same plane. So definitely if this is I, this one is also going to be I. So I plus I is 2I. 2I need to be what? mr square. 2 times I, that's going to be what? mr square. So I is going to be what? mr square by 2. And you can see that here. And now I got the moment of inertia with respect to this axis. Okay. Now that means I know the moment of inertia with respect to this axis. What this is? This is mr square by 2. And here this is the another one. So here again, parallel axis I am going to be my friend here. So here you can see the distance of separation is what? R. The moment of inertia with respect to this axis is mr square by 2 plus mass is m. Distance of separation is r square. So here this is going to be what? 2mr square plus 1. It's going to be 3mr square by 2. And you can see that relation here. I hope you are getting me right. Okay. So the same way for a disk we are going to do. For the disk with respect to its center of mass, it's going to be mr square. Center of mass and perpendicular to the plane, it's going to be half of mr square. Now with respect to this, here it is going to be half of mr square plus m into r square. You can see the relation. It's what? 3 by 2 times m into r square. Same pattern. Now I am going to find out the moment of inertia with respect to any of these two. So here with respect to this particular axis, it is what? mr square by 2. Alright. Now with respect to any one of this, it's going to be what? mr square by half of this. That means mr square by 4. Now parallel axis theorem is going to help me. How? mr square by 4 plus mr square. So here this is going to be 5 times mr square by 4. Have a look. Getting my point? Getting my point? Yes. The next is for a thin rod. If it is rotated with respect to one of the edge, it's going to be ml square by 3. And if it is rotated with respect to the center, it's going to be ml square by 12. Very, very important. With respect to one of the edge, it's going to be ml square by 3. And with respect to the center, it's going to be ml square by 12. Next, for a solid cylinder with respect to the axis, it's going to be mr square by 2, exactly same as that of a disk. All right, and with respect to one of the edges, so here what was there for the disk, exactly the same will repeat. Okay, now for a rectangular plate, do you remember for a rod it was ml square by 12? Here it's going to be the same, ml square by 12 plus mb square by 12. Once you simplify, it's going to be m into L square plus b square by 12. All right. Next one is for a thin spherical shell. For a shell, it's going to be 2 by 3 mr square with respect to the center, hollow sphere. And for a solid sphere, it's going to be 2 by 5 mr square. It's 2 by 3 and 2 by 5. Okay. So first of all, with respect to the center, diametrically it's going to be 2 by 3 mr square, and with respect to the tangent, against the parallel axis theorem only, you can see 2 by 3 m into r square plus m into r square. So this is how 5 by 3 mr square it came here. All right. The next one is solid sphere. It's 2 by 5 mr square, and with respect to one of the edges, what you are going to do is 2 by 5 mr square plus mr square, parallel axis theorem. R is the distance of separation. 5 plus 2, 7. So 7 times mr square divided by 5. This is that relation. I hope you got it right. Okay. The next one is torque acting. Okay. So if, let this be a particular a rigid body, and let this be the axis of rotation, and at this particular position, say R, let a force F be acting like this. So here this is the direction of position vector, and here this is F. Now the torque experienced by this particular rigid body is going to be R cross F. Okay, and that can be written as RF sin theta n cap. So here, if this is the rotation, direction of rotation, the torque is going to be in the upward direction. So here this is going to be the direction of torque, that you must understand. And the relation between torque and moment of inertia, this is very important. Very important. Okay, the relation between torque and moment of inertia is torque tau, that's equal to I into alpha. How to keep this in mind is, we all know that F is equal to m into A. The role of force is being done by torque here, role of mass is done by moment of inertia there, and role of acceleration is done by angular acceleration. So if F is equal to m into A, then torque tau is going to be I into alpha. Dimensional formula is going to be same as that of work done, that is ml squared t raised to minus of 2. Next one is angular momentum. Angular momentum is nothing, moment of inertia multiplied by angular velocity, or for a particle, if you consider, it's going to be m into v into r. In vector form, if you want to say, it's going to be r cross m into v. And if there is no external torque acting, law of conservation of angular momentum, if there is no external torque acting, then the angular momentum of the system will remain constant. And if there is a torque acting, then the rate at which the angular momentum is changing, I repeat, the rate at which the angular momentum is changing, that is going to be d by dt of L. That is going to be the torque experienced by the body with respect to the axis of rotation. All right. And this I already told you, law of conservation of angular momentum and how they are connected. And the next one is equilibrium of rigid body. Equilibrium of rigid body means if the net force experienced is 0 as well as the net torque is 0, then we used to say that that particular body is an equilibrium condition, and couple is nothing, it's same as that of torque, only two equal and opposite forces acting with respect to the axis of rotation, which will which can trigger the rotational motion to a body is known as couple. And how to calculate the couple or torque experienced is any one of the force with respect to the axis of rotation multiplied by the perpendicular distance of separation will give the torque acting. All right. And the next one is center of gravity. I repeat, center of gravity. It is, see, as per the definition, if a body is supported on a point such that the total gravitational torque, see, the total gravitational torque about this point is 0. Okay, a body is supported onto such a point, okay, so that the net torque experienced by the body is what? 0. Then that point is known as what? Center of gravity. Okay, and if the acceleration due to gravity acting on all the point is the same, then center of mass and center of gravity is going to be the same. But if we are having an object which is comparatively very bigger, and just because of that the acceleration due to gravity experienced by different mass present in the body is different, in that case it's not going to be so, because acceleration due to gravity, it changes with respect to height. So special case, if acceleration due to gravity is constant, the center of mass is going to be center of gravity. What is center of gravity? The gravitational torque with respect to a given point is going to be 0. Okay, then if the gravitational torque experienced by the body is going to be 0 with respect to a particular point, then that particular point is known as what? Center of gravity. Okay, and the next is angular impulse. Angular impulse is nothing, the total change in angular momentum. That is, in two ways we can represent that: integral of tau times dt within the limit t1 to t2, or, and definitely that is going to be what? LF minus of Li. LF stands for final angular momentum and Li stands for initial angular momentum. And this is again very important thing, that is rotational kinetic energy. Rotational kinetic energy is the kinetic energy of all the particles present in a body that is rotating. Okay, a body, if a body is executing rotational motion, if we consider the rotational kinetic energy of all the kinetic energy of all the particles, the summation of all together will give what? Rotational kinetic energy. And if I have got a rigid body whose moment of inertia with respect to axis of rotation is I, and the angular speed at which the system is rotating, I mean the rigid body is rotating, is omega, then the rotational kinetic energy is going to be half of I into omega square. That's going to be the rotational kinetic energy. All right, and here I have got something very important. All right, in almost all year, okay, a question somehow connected to this, sometimes in terms of acceleration, sometimes in case of speed, sometimes in terms of the time taken. Definitely one question used to be there all the time. So I will tell you a shortcut how to memorize this. The key part is this one. The key part is this one. That means the acceleration. Okay, I am going to tell you a shortcut how to memorize this. If I have got an object kept like this, you might be wondering, this is the case of rolling, and why this guy is creating a rigid body over here. I told you, I'm going to tell you something important which will help you to keep this particular equation in mind, and if you know this particular expression, you can easily handle the rest of. Okay, if I have got a body like this, allowed to slide down, there is no friction. In that condition, you know that down the plane, this is going to experience an acceleration of g sin theta, because g cos theta is going to be the acceleration component here, and g sin theta is going to be the component of acceleration acting in this direction. Okay, now for a body which is rolling down the wedge, making an angle theta with respect to the horizontal, the acceleration experienced by that body A is going to be, this is very important, it's going to be the same thing, that is g sin theta divided by, okay, in the denominator you have got just one term, 1 plus, okay, k square upon r square, where k is radius of gyration and r is the radius of the body. This is the only thing that you must understand. There it is g sin theta, and here it is g sin theta upon 1 plus k square upon r square. Okay, now how this particular relation is going to help you in all other part? We all know that once it comes down, once it come down, all right, at the bottom, once it reach here, I can say that this is going to travel a distance of what? S. I mean, down the plane along this direction, it's going to travel a distance of what? S. And if it is allowed to start from state of rest, then I can say that down the plane it's traveling a distance of what? Half of gt square. Okay, this is the case where we consider it as a single block. And if I rearrange this, it's going to be 2s upon g under root. That will give the time taken. All right, and just have a look. 2 times s upon, instead of acceleration here, you know, we took it as what? Half of gt square. I mean, this stands for what? Acceleration a. I repeat, this is acceleration a. Fine. So this g, I mean, again I repeat, this is not acceleration due to gravity, this is acceleration a. Now this acceleration a is going to be replaced by this particular term. So there it is going to be what? G sine theta. Okay, it was divided by 1 plus k square upon r square. So definitely it will go to the top. 1 plus k square upon r square. And you can see the time. This is the expression for time, isn't it? Now, after traveling through a distance of again s, okay, what will be the speed of the body? We all know that v square equal to u square plus 2as, general expression for a particle sliding down. But in our case, a is going to be this. What? A is going to be what? G sine theta upon 1 plus k square upon r square. This is our acceleration. All right, so I will go for that. V square equal to u is 0, 2 into what is a? G sine theta all divided by 1 plus k square upon r square into s. So definitely v is going to be what? Under root of 2 times g into sine of theta into s all divided by 1 plus k square upon r square. This root include this one as well. Okay. Okay. Now have a look. Here you have got the expression for v. Okay. So entire thing you can connect using that single expression. So that is why I said it is very, very, very important. All right. So you might be wondering what to do for h. So definitely what to do for h. There also I can help you. This is theta. I took this entire length as s, and here this is what? H. And you know that this h is equal to what? H is equal to s times sine of theta. So you can replace s in terms of h as h is equal to s sine theta. Okay, now s can be replaced as h by sine theta. All right. And the next one is, what about the minimum friction required for a body that need to slide down the plane making an angle theta with respect to horizontal? So there the minimum coefficient of friction that need to be equal to I into A. I stands for moment of inertia, A stands for the acceleration. All right, I into A upon r square divided by mg cos theta. That is the minimum friction required. And the next one is, what about the total rotational kinetic energy? Okay, the total kinetic, not total rotational kinetic energy, total kinetic energy possessed by the body. Definitely the total kinetic energy possessed by the body, that is going to be kinetic energy Ke is going to be kinetic energy due to rotational motion plus kinetic energy due to translational motion. All right, kinetic energy due to rotational motion can be written as what? Half of I into omega square, and here this is going to be half of m into v square. And here also I want to tell you something important, that is, see, if a body undergoes pure rolling, We all know that the velocity of center of mass is going to be what? Vcm, and here the angular speed at which this is rotating is going to be omega. So the kinetic energy rotation, that's going to be half of I into omega square, and kinetic energy translation, that's going to be half of m into v square. And we all know that I, that is m into what? K square. Let me consider that over here. So kinetic energy rotation, that's going to be half of, instead of I am going to have it as what? M into K square. Alright. And for pure rolling, we know that Vcm equal to R into omega. So for omega square, I can have Vcm square by Vcm square divided by R square. And what about translational kinetic energy? Definitely that is going to be half of m into Vcm square. Now the total kinetic energy is going to be the summation of all this. Now here I have got m into Vcm square by 2 as common. Alright, and here it's going to leave 1, and here this is going to leave what? K square by R square. So here this is going to be the expression for total kinetic energy. Okay, questions related to ratio of total kinetic energy to rotational kinetic energy, ratio of total kinetic energy to translational kinetic energy were there many a times. So you must be able to understand how to proceed with that. Alright, and here I told you about the pure rolling. Okay, exactly that is mentioned here as well. If a body is undergoing through pure rolling is the special case of rotational motion plus translation motion, and I am going to tell you how that's going to be a special case. For a translation motion, each particle is going to have the velocity like this, and exactly that is going to be what? Vcm. And for rotational motion, the velocity of the particle is going to be like this. And for pure rolling, it's going to be the combination of both these. That means I need to place this one over here. So once I place this one over here, I can see the bottom part is going to have a velocity component like in this way. Here it's going to be what? V, only this particular part, and here this is going to be the summation of this one as well as this one. If it is pure rolling, this particular point, that is going to be at state of rest. And if that is going to be at state of rest, that means this particular component in the backward direction and this one in the forward direction need to be the same. That means both these need to be the same. Alright, that means if this is the same, the velocity of the topmost point is going to be what? 2 times v, and here this is going to be v, and this particular part is 0. So basically what this is velocity of center of mass, and that's what I said here. Once it is a case of pure rolling, then Vcm is going to be R of omega, and the point here that's going to be at state of rest, and the particle over here that's going to be 2 times Vcm, and particle over here it's going to be Vcm here as well as Vcm in this way. There the particle is going to have what? Under root of 2 times Vcm, and here Vcm in the upward direction, Vcm in this way. So the resultant is going to be again under root of 2 Vcm here. Our next chapter is gravitation. Okay, so here we are going to just give a small introduction to gravitational force first. Gravitational force is one among the 4 fundamental forces. You might have studied in the very first chapter of grade 11. Okay, so there 4 fundamental forces are there. First one is gravitational force, next one is electromagnetic force, next is strong nuclear force, and another one is weak nuclear force. Okay, why we are discussing this thing is, there many a times there were questions comparing gravitational force to other fundamental force. That is the only point of discussion of this slide over here. Okay, so while comparing with the other forces, obviously the magnitude of the forces and the nature of force, like whether it is attractive, repulsive, obviously the comparison will be coming. So we will be discussing that important comparisons, okay, which were asked many a times in the competitive examinations here. So out of that, the very first ones that comes over here is, it is always an attractive force. It's always an attractive force. That is the one point over here. And as I told you, it's always an attractive force. Then let's discuss what's going to be that force. So if you have got two masses like m1 and m2 at a distance of separation of small letter r, then the first body is going to experience a force due to second one, that I am going to mark it as F12, force experienced by 1 due to 2. And here this is going to be force experienced by 2 due to 1. Okay, and the magnitude of these two forces, F12 and F21, the magnitude of these two forces is going to be the same only, but direction is obviously opposite. Now that force F is equal to capital G, that is universal gravitational constant, into m1 m2 divided by r square. And what is going to be the value of universal gravitational constant? It is 6.67 into 10 to the power minus of 11. Okay, unit is going to be Newton. Just have a look here. This is Newton. Here this is meter square. This will come down. So that's why upon kilogram raised to 2. Or I can say Newton meter square kilogram raised to minus of 2. Okay. And this particular, as the name there itself, it is there, universal gravitational constant. That means that is a constant which is same everywhere in the universe. Okay, so that is not going to change its value. It's going to be everywhere. That means at Earth also it's going to be the same, in some other place in the universe also it's going to be the same thing. That's why we call it as universal gravitational constant, isn't it? And obviously the dimensional formula is there. And one more thing is, as I told you, this capital G, universal gravitational constant, it's not going to change the value with respect to the place or with respect to the reference frame. And on the top of that, there is one more speciality of this particular constant, that is, obviously constant means one which is not going to change, means it's going to be the same for all. Now I want to specify that point here once again, that is, this value of capital G, it does not depend upon the mass, it does not depend upon the distance of separation also. Since it is mentioned over there, that's why I'm just again telling each and every details of that one. Okay, now I told you we will be going for a comparative study, and here it begins. The first one is, gravitational force is always a central force and it is conservative. Okay, nuclear force of attraction, it's a non-central force, but here it is a central force and that is a conservative force. That is point number 1. And second one is, it is the weakest out of all the 4 fundamental forces. Okay, that is next one. And here exactly comes the comparison between electrostatic force and the nuclear force. While comparing with the electrostatic force, it is weaker by 10 to the power 36 times. While comparing with the strong nuclear force, alright, that is 10 to the power 38 times weaker. Alright, the next one is this force of attraction. This force of attraction, it is applicable to all the bodies irrespective of their shape, size and position. That means 2 sphere of mass kept at a distance of separation, 2 cylinder of same mass kept at the same distance of separation will be experiencing same gravitational force of attraction. Okay, so that is the point over here. And the another one is what actually makes the planet move around the sun. Okay, fine, definitely that is going to be the gravitational force of attraction between the planet and the sun. If I have got sun here and planet, so the gravitational force of attraction is the one which provides the necessary centripetal force. So if we want to calculate the orbital speed, radius and all, definitely we are going to use this concept. So each point mentioned over here, it has got a significance. That's why we are telling that in detail. Okay, and the next one, I already told about point number 6 over here. See, while discussing about force or experienced by particle 1 as well as particle 2, I marked this as F12 as well as F21. So if F12 is action, then F21 is the reaction. Alright, so that is what mentioned over here, point number 4. Point number 4 says that Newton's third law of motion holds good for Newton's law of gravitation between two bodies, action reaction pair. So F12 is going to be same as that of F21, but the directions are different. And one more thing, this action and reaction, F12, if I take it as action, then F21 is going to be the reaction. Okay, and always please try to understand this. Action and reaction acts on two different bodies. I repeat, action and reaction acts on two different bodies, so this never cancel each other. If it was acting on same body, then only the possibility of cancellation was there. Since action and reaction is acting on two different bodies, they are never going to cancel each other, so never assume that the net force experienced by this body is zero. No, not at all. All right, and again need to highlight 3 more points out of the last list. That is, unlike electrostatic force, this particular gravitational force of attraction, it never depends on the medium. Never depends on the medium. Depends on the medium. Questions were asked from this. Okay. Second thing is, it is conservative in nature. Definitely path related questions will be there. Okay, and if that questions come, you must understand, if you take a body to a particular height in this path, or if you take a body to a particular height in this path, or if you take a body to a particular height in this path, work done is the same. Okay, it's conservative in nature. And next one is, it is central force. Like whenever you are having a spherical structure like this, okay, and if you want to find out the gravitational force of attraction between another mass kept here, what you can do is, you can assume the entire mass of the sphere to be concentrated here, and the entire mass of the second sphere be concentrated at the center. Now you can treat these two are 2-point masses. Okay, so in that condition, if this center to center distance, if I can mark it as capital D, then let capital M be the mass of this and a small letter m be the mass of this one. So I can now mark this as capital M and small letter m, 2-point masses kept at a distance of separation D, and the gravitational force of attraction between these two masses is going to be G capital M small letter m divided by D square. All right, fine. Moving to the next slide, they're telling about the central force. I already told you what is central force. Here it's going to act along the center to center. And next is acceleration due to gravity. Any mass on the Earth's surface will experience a force which is pointing towards the center of the Earth, and the force by which Earth pull any object on its surface towards its center, we call it as what? Gravity. We call it as what? We call it as gravity. And if F suffix G is that gravitational force, we all know that F is what? M into A. Now this acceleration is experienced by this body only because of this gravitational force of attraction, and this acceleration due to gravitational force is known as acceleration due to gravity. Fine. Since force is a vector quantity, and you know that force is, I already told about that, this force is pointing towards the center of the Earth, acceleration due to gravity is also going to be what? A vector. That is also going to be a vector. And what is going to be the direction? In the same direction of gravitational force. And where the gravitational force was acting towards? It was acting towards the center of the Earth. So the direction of acceleration due to gravity is also going to be towards the center of the earth. All right. So obviously the dimensional formula of acceleration, it is LT raised to -2. Here also it is going to have the same thing, and obviously unit is meter per second square. Okay. So the next is again some important points regarding acceleration due to gravity. Okay. Don't think this is an unnecessary theoretical points. Again, he's stretching it as anything. No. These points will help you a lot while dealing with the numericals. Okay, it will be very helpful. So never skip these details. The first one is acceleration due to gravity is independent of the mass. For example, if a 100 kg mass is falling towards the earth, and let be another feather also falling towards the earth, the acceleration experienced by these two masses is going to be the same. That is point number 1. Okay. Second one is acceleration due to gravity. It changes with respect to height, and it will change with respect to the depth as well. Okay. On the surface of the earth only, we take it as 9.8 approximately. And if we go towards higher altitude, it will decrease. And once we go down from the surface of the earth, if we travel towards the center of the earth, there also the value of G will be changing. That is point number 2. Okay, this I already told you. On the surface of the earth, we will be taking it as 9.8. all right. Next one is its comparison with respect to that of the moon and that of sun. Related to moon, there were questions many a times. If we take the acceleration due to gravity on the surface of the moon, approximately it is 1/6 of gravitation, acceleration due to gravity on the surface of the earth. And as per the calculations, if we consider the acceleration due to gravity on the surface of sun, it is 10 to power 27 times greater than that of acceleration due to gravity on the surface of the earth. If we consider the planets, Mercury is the one which is experiencing the least acceleration due to gravity. All right. And next is what going to be the mathematical expression for acceleration due to gravity on the surface of the earth. For that, you know how to get it. You just need to keep a mass on the surface of the earth and mark this as capital R. I already told you, if we are having a mass outside a spherical body, we can treat this as 2 point masses. So the force experienced by this body is going to be force experienced by this mass of small letter m. That's going to be what? G capital M small letter m divided by what? R square. And I may take it as what? M into G. So this m and m will cancel each other. That will give the same relation here. Okay. And here mass of the earth. Okay. To get into the numerical value, mass of the earth, you need to take it as 6.4 into 10 to the power 24. And the radius of the earth, you may take it as 6.4 into 10 to the power 6 meters. Okay. Now, what are the factors that affects the value of acceleration due to gravity of the earth? So here we are going to discuss about the earth only. Definitely the shape. Okay, fine. The earth is exactly not spherical in shape. Okay, it's something like this. Okay, you can press it like this. So definitely here the equator, radius of the equator is comparatively greater. Okay, and the distance towards the pole, if I take it as r suffix p, so it's very clear, r suffix p is less than what? R suffix e. All right. Since r suffix p is less than r suffix e, we know the equation. What is g? G was capital G m upon r square. Okay. So if I take gp, then this is going to be what? G capital M upon rp square. And if I take g suffix e, That's going to be G capital M upon R E square. So R is greater than what? RP, right? Which means it's going to be minimum at the equator and maximum at the poles. Questions were there. It's going to be minimum at the equator and maximum at the poles. Okay. The next one is, so here this was because of the shape and here this is because of the rotation. Due to rotation, if I consider a mass here, fine. So the gravitational force, if this particular system was stationary, then definitely it should have been m into g. But we know that it's not like that. Earth is rotating. So once it is rotating, there will be an outward force acting on this body. And while considering that outward force, the resultant acceleration due to gravity experienced by that body, it's going to be g dash. Okay, it's going to be g dash. And what's the value of g dash? G dash is going to be g minus of, I repeat, it's going to be g minus of r into, I repeat, it's going to be g dash is going to be g minus of r into omega square cos square theta. Okay, it's going to be omega square cos square theta. So students, while try to memorize these relations, they generally used to ask me, sir, I used to get confused whether it is r omega or omega square r or r square by omega. We used to get confused like that. So how we can? Definitely, we all know that acceleration A, that is r omega square only. Okay, so here this is acceleration, so here also this need to be what? Acceleration only. So dimensionally these two need to be the same. So if it is A minus B, definitely A should be having the same dimension of that of B only. So here we can't have r into omega, because r into omega is not acceleration, it is r omega square only is acceleration. Alright, so keep that in mind. It is r omega square because it is, after all, it's acceleration, and cos square theta term is there. Okay, and theta, it's here, it's not marked as theta. Here the angle is taken as lambda, so this is that angle. Okay, so there was one question: what happens if the earth stop rotating? Okay, now if the earth stop rotating, definitely from this particular part, from this equation, this particular part is going to be what? Missing, because omega is going to be 0 there. So definitely g dash is going to be g. Okay, now how the changes vary? So the change is going to be this. At any particular point, the change is going to be this. That means if I take this as the equator, so at the equator lambda is going to be 0 and cos 0 is what? So it is going to change by what? R omega square. Okay, now at a particular point here, and I take the theta angle as what? 45 degree, then it's going to change by a value r omega square by root 2. Okay, questions were there, that's why I'm telling. So how the changes will happen if the earth stop rotating? So this is immediately you can come to a conclusion from this relation itself. Okay, so this is that part which is going to determine through what value the change is going to happen. Definitely it depends upon the angular position of the point that we take with respect to the equator. Okay, now next one is the altitude. With respect to the altitude, the standard expression is g dash is equal to g upon 1 plus h by r the whole square. I repeat, g dash is equal to g upon 1 plus h upon r the whole square. That is the standard expression. And if h is very less than r, I repeat, this is the standard one, and here this is the special case. And what is that special case? If h is very less than r, then you may take it as g dash is equal to g into 1 minus of 2h upon r. G dash is equal to g into 1 minus of 2h upon r. I repeat, this is a special case. This is the standard one. Okay, this is the standard expression. Don't forget that. All right, and with respect to the depth, how it varies is g dash is equal to g into 1 minus of h by r. G dash is equal to G into 1 minus of H by R. And here in special case, you can see it was G is equal to G dash is equal to G into 1 minus of 2H upon R. But special case, I repeat once again, this was special case. And here with respect to depth, you can see it as G dash is equal to G into 1 minus of H by R. Okay. And next is gravitational field. Gravitational field is the space around any mass. Within that space, another mass will experience gravitational force of attraction. That is what we call it as gravitational field. And there, gravitational field intensity or intensity of gravitational field means force experienced by 1 kg mass kept at any point in the gravitational field. For example, let us consider Earth, and within the gravitational field of Earth, let me consider a mass small letter m. The gravitational force experienced by this mass is going to be F equals capital G capital M small letter m upon what? R square. And if at the same point, if I place a 1 kg mass, then what is going to be the force experienced by that mass? Obviously, it's going to be F upon m. And we call this as intensity of gravitational field. Alright, that is represented by E suffix G, or in some textbook you can see the same represented by capital I also. Okay, fine. The most interesting part is it's exactly going to be same as that of acceleration due to gravity. Almost seems to be the same. If we consider it for the Earth, it's going to be exactly same as that of acceleration due to gravity only. Because of that, you can see the dimensional formula, the unit, everything is going to be the same. Fine. All right. So here this is the mathematical relation, and this was the what is the significance of gravitational field intensity. Moving to the next, gravitational field intensity due to different mass distribution. Numerically, this particular part is again going to be very important for you. First one, due to point mass. So here we discuss the case of the Earth. All right, it's going to be the same here. Fine, because again I repeat, if we take any point outside the sphere, we assume that the mass is focused at the center. The same concept is used here. A point mass, capital M, at a distance small letter r, we are having another mass. Okay, fine. And let that mass be, let this be the point. Okay, let this mass be smaller m. Then as what we discussed, force experienced is going to be what? G capital M smaller m by r square, and force upon mass, that is going to be the gravitational field intensity. So here also you are going to get the same expression, that is Gm by r square. You are going to get the same expression. Okay, moving to the next. Here comes the very first one, that is due to uniform solid sphere. It is uniform solid sphere. My dear students, this is a super important area. Okay, so here we are having 3 points. First one is R greater than capital R. That means it's going to be outside the sphere. Okay, next is R equal to smaller r equal to capital R. That means on the surface. Next one is small letter r is less than capital R. So inside. I believe you are getting me right. Okay, 3 points. So here I am going to consider a solid sphere. Okay, here this is the case, small letter r greater than capital R. Next one is this, small letter r equal to capital R, and here this is the last one, small letter r less than capital R. This is going to be the first one we are going to discuss. This is going to be the second, and this is going to be the third one what we are going to discuss. All right, have a look. It is gm by small letter r square for point outside, and gm upon small letter r will become capital R only. That is the only difference here. Gm upon capital R square for the second one, and the last one is gm into small letter r will appear here, and on the denominator it's going to be r cube. Okay, next is spherical shell. For spherical shell, the important part you must understand is, see, these two relation is going to be the same. Okay, and here this is going to be what? 0 for a spherical shell. Fine. So in the spherical shell also the situation is the same. So here this is the shell what I want to consider. All right, now from the center we are moving towards outward, r greater than capital R. Here at the center r equal to capital R, and here this is small letter r less than capital R. Okay, so these are the cases. So you can compare the thing. And the next one is due to uniform circular ring. Okay, so here you must understand uniform circular ring means the case is something like this. This is the ring what I am considering, and this is the axis of the ring. Okay, so the ring is kept on y z plane, and here this is x axis. So here this is x axis, here this is y axis, and here this is z axis. Okay, so in that case, at a distance small letter r from the center, that means if I consider a point here which is at a distance of small letter r, and capital R is the radius. Okay, gravitational field intensity is going to be gm into r, exactly the same thing there, gm into r upon r square. So here it's written as small letter a. All right, so here this is written as small letter a there, that is only part, is going to be a square plus r square raised to 3 by 2. All right, and on the surface again I is going to be what? 0. All right, next is gravitational potential. Gravitational potential is defined as work done in bringing 1 kg mass from infinity to any point within gravitational field. I repeat, work done in bringing 1 kg mass from infinity to any point within the gravitational field. And always understand one thing, the gravitational force, it's always an attractive force. Okay, so the work done by the external agent is always going to be what? Negative. Okay, so wherever we deal with gravitational field, not gravitational field, gravitational potential and gravitational potential energy, you are going to get that as a negative value because the force is attractive in nature. If the force was repulsive, then there the potential energy as well as potential should have been positive. But if the force is attractive, then the gravitational potential as well as gravitational potential energy, it's always going to be what? Negative. All right, so here I told you work done in bringing 1 kg mass. So if W is treated as work done in taking a mass from infinity to any point, and if m kg is the mass, then gravitational potential at that particular point, V suffix g, it is marked as minus of g m upon small letter r, where small letter r is the distance from the center of the earth. For example, let this be the earth, mass is capital M. Okay, here this is the center, and here this is the distance. Okay, so here the gravitational potential, V suffix g, we got it as G capital M upon small letter r. All right, dimensional formula is going to be L square T raised to minus 2, because work done is, dimensional formula for work done is m L square T raised to minus of 2 upon mass it is going to be, isn't it? Upon mass it is going to be, so this will cancel each other. So the dimensional formula is going to be what? L square T raised to minus 2, and here it is work upon mass, so definitely it's going to be a scalar quantity. All right, the next is gravitational potential energy. Okay, there let me consider two masses, say m1 and m2. The work done by the external agent to assemble the masses like this, okay, ignoring all other interactive forces, the work done by the external agent to assemble the masses like this, that work is treated as what? Gravitational potential energy of two mass system. So here we are considering Earth and some other mass, alright. So in that condition, the work done is going to be what? Work done is going to be minus of G capital M small letter m upon R. Okay, here this is the Earth, fine, and I am having is mass small letter m kept at a distance of separation of small letter r. That is the condition. So here you can see the gravitational potential energy of two masses. I am taking the case of Earth and a mass m at a distance of small letter r. You can see exactly the same thing here. Okay, now you can see one more relation here. Fine, nothing. Here small letter r is replaced as capital R plus H. What does it mean? Here it is capital R, here this is H. So small letter r is what? Capital R plus H only, isn't it? So if small letter r is replaced by small letter r is replaced in terms of capital R and H, where H is the height from the surface of the Earth, so definitely the relation is going to be G capital M small letter m upon, instead of small letter r, it's going to be capital R plus H. Alright. The next one is gravitational potential energy of two particle system that we already explained here. The same expression you can see here as well. The potential energy is going to be minus of G m1 m2 upon small letter r. Alright. The next one is, what if you have got more than two particle system? Okay, here you can see a case is considered where four masses are there. So in that case, what you need to do is, we have got 1, 2, 3 and 4. Okay, so you need to take the combination of 1, 2, 1, 3, 1, 4 first, and after that 2, 3, 2, 4, and after that 3, 4. Alright, so it's going to be 1, 2, 1, 3, 1, 4, 2, 3, 2, 4 and 3, 4. So 1, 2, 3, 4, 5, 6. So there's going to be a set of 6. Alright, and how to identify that? What was the number here? Masses were 1, 2, 3, 4. 4 masses was there. Alright, now how many sets are here? 1, 2, 3, 4, 5, 6 sets are here. So 4 mass was there. So we can go for a general expression, that is n into n minus 1 by 2. Here n is 4. Okay, so 4 into 4 minus 1 is 3 by 2. 3 2s are 6. Exactly, you can see the same number here. Okay, so if n number of masses are there, then the group that's going to be there is going to be n into n minus 1 by 2. Alright, now this is the group that we got. Now the potential energy of the system, how you are going to calculate is going to be U equals minus of G, that is common. Alright, so here it was 1, 2, so here you need to go for M1 M2 divided by R12 plus next is 1, 1, 3, isn't it? Here this was 1, 2, 1, 3, 1, 4. So here this is going to be what? Here this is going to be M1 into M3 divided by R13 plus M1 into M4 divided by R14. Alright, like that it will go up to M3 M4 upon R34. Alright, because here the last one was what? M34. 34 was the group, so it's going to be M3 M4 upon R34. That's going to be the final expression. I hope you got it right. Next is gravitational potential for different bodies. The way we discussed about gravitational field intensity for different bodies. Here we are going to discuss about gravitational potential for different bodies. Again, this is very important. So the first one is due to uniform ring. Okay, so here we are going to take it at a particular point, all right, I mean at a distance of small letter r, and another one we are going to take it exactly at the center. Don't forget, this is a case of ring, uniform ring. So for uniform ring, it's going to be minus of gm upon under root of a square plus r square. Minus of gm upon under root of a square plus r square, and once we take it at the center, definitely r is going to be 0, and that's going to be minus of gm by a only. And if we go for a spherical shell, here r greater than r equal to capital R, and inside the surface, 3 cases, same as that what we discussed there in case of gravitational field intensity. Here outside the sphere, it's going to be minus of gm by small letter r. On the surface, small letter r is going to be capital R, and here again inside it's going to be minus of gm by r only. All right, okay, it's spherical shell, don't forget it is a case of spherical shell. And here comes due to uniform solid sphere. Okay, due to the uniform solid sphere, for small letter r greater than capital R and small letter r equal to capital R, it's going to be same as that of the shell. The only difference is inside. There it is going to be minus of gm upon capital R into 3 minus of r by capital R, the all square. All right, here this is inside the spherical shell. Inside the spherical shell. Okay, this is going to be the case, and here this is how we can show the graphical variation for the same. Is that fine? Moving to the next, that is relation between gravitational field and potential. Basically, you must understand one thing. dv, that is going to be minus of E dot dr. This is the standard relation. Okay, if you consider this separately along x-axis and y-axis, you can see the further variations here. All right, the next one is Kepler's law. Okay, Kepler's law of planetary motion, that is what we call for this topic. So the first law says that every planet move in an elliptical path round the sun, and sun is going to be there at one of the focus, either it could be here or either it could be here. And there are, this particular axis is known as major axis, and here this is known as minor axis. This distance is known as distance of semi-major axis, and here this is known as distance of semi-minor axis. So here this is semi-major axis. All right, next one, I mean the second law says that if this planet move from here to here, this is the area swept by the position vector, and if I provide same time interval, this is going to be the area swept by the position vector. Now second law says that these two areas is going to be the same. Okay, fine. So in other terms, aerial velocity is going to be constant, and mathematically we can prove that dA by dt, okay, area swept in unit time, that is L upon 2m, and that is a constant where L is the angular momentum. All right, the next is Kepler's law number 3, and here this is going to tell about the time period, and what it says is square of time period is proportional to r cube. Here instead of r you can see small letter a, it's the same thing only, fine. So square of the time period is proportional to r cube. That means if the radius is changing, then the time period is going to change like this, t1 by t2, the all square is going to be r1 by r2, the all cube. Okay, so that is Kepler's third law. Fine, moving to the next. Now we are going to discuss about the satellites. All right, first of all we need to tell about the time period of the satellite. Okay, nothing, there is it's not at all a complicated topic, very easy topic. Okay, please try to understand something like this. Let this be the Earth and let this be a satellite, and let the orbit be of distance small letter r. Okay, orbit is at a distance of small letter r. Now, in the beginning I said the necessary centripetal force is going to be provided by what? The gravitational force. So if m is the mass, then the necessary centripetal force mv square by r is going to be provided by the gravitational force of attraction between the Earth and that planet only, isn't it? So here this one and this one will cancel each other, this one and this one will cancel each other. So what's going to be the value of v? That's going to be root of gm by r. So v is going to be root of gm by r. So once it complete a motion, complete circle, the distance traveled is what? 2 pi r. Distance traveled is 2 pi r. And what is the speed? Speed we got it as under root of gm divided by small letter r. So definitely that is going to be the time period, isn't it? It is as simple as that. Fine. Now if you want to replace these terms in terms of height h, okay, in terms of small letter g, you can have further options like this. Alright. Next is it's the same thing only. Now regarding artificial satellites, these terminologies are bit important, so you need to keep this data. It's not that very important, but these terminologies, if the questions comes, you must at least understand what you mean by geostationary satellite, what you mean by polar satellites and all. Fine. So geostationary satellites means basically if we observe the satellite from the Earth, we feel like that is not at all changing its position, and always is going to be at a stationary position. So basically this is used for communication purpose. Alright. So what happens is there, if the Earth is rotating with an angular speed of omega, alright, and if we want a body need to be always at this particular position, alright, now the angular speed of this and the angular speed of this one, it need to be the same. Okay, so if we set such an orbit, if we identify such an orbit and place a satellite there with the same angular speed, so always it's going to be what? In the same position only. Those type of satellites are known as what? Geostationary satellites. Another name is parking satellites. Alright, I told you the main purpose of this one is what? Communication, because the signals what we are sending, it must be received by the antenna over there and it need to be transmitted to some other part. So we want it to always to be at a constant position, otherwise the entire configuration is going to change. Alright, so here we prefer it always to be on the equatorial orbit. Okay, the another one is polar satellites. The main purpose of this one is to predict the climate changes. Okay, so there is going to be placed on the polar orbits only. Alright, so geostationary satellite, equatorial orbit, and here you can see it was placed at equatorial orbit, and the polar satellites, which is used for communication, which is used for the prediction of climate change and all, it is placed on polar orbits. Alright, so the next is orbital velocity. We already derived this relation over there. Fine. So here, while calculating the time period, we already derived this particular expression. The same thing is repeated here once again. So it's nothing, the speed by which, like let this be Earth, the speed by which the satellite orbit round the Earth, that is what we call it as what? Orbital velocity. And I already told you how to calculate that. mv square by r is going to be provided by the gravitational force of attraction between the Earth. Solving this, you will get this relation. That's all. Okay. The next one is the energy of the satellite. Okay. While discussing about the energy of the satellite, you must understand one thing. So here, it's moving with a speed of say v0 or v0, and it is within the gravitational field of the earth. So definitely while telling about the energy, we need to consider the kinetic energy because of its motion, and definitely due to the position within the gravitational field, definitely it will be having what? Potential energy also. So here the total energy is going to be the summation of kinetic energy plus potential energy. So the kinetic energy is going to be G capital M small letter m upon 2r, and the potential energy is going to be minus of G M capital minus of G into capital M small letter m upon r. You must not miss this particular part. The magnitude of potential energy and magnitude of kinetic energy, if you closely watch, you can see twice the magnitude of kinetic energy is equal to the potential energy. I repeat, twice the magnitude of kinetic energy is equal to the potential energy. So that particular part need to be considered over here, and you can see the total energy of the satellite, it is minus of G into capital M small letter m upon 2r. Alright, you can see it is negative again. Alright, and next is time period of revolution. I already told you how to calculate the time period of revolution. Alright, so here the only variation is just because here we have replaced G capital M small letter r m with capital R, H and V naught. That is the only change over here. Rest all exactly the same as what we derived the time period in the previous slide. Alright, and it's again the same thing only. Now next is the binding energy. Okay, so binding energy is nothing. It is the energy by which a satellite is bonded towards the earth. That is binding energy, and that is equal to, magnitude wise, that is equal to the total energy of the satellite. And if you want to remove that satellite, if you want to remove the satellite from the gravitational field of the earth, definitely we have to provide the total energy. And what was the total energy? It was minus of G at a distance of small letter r. The total energy was minus of G capital M small letter m upon 2 times r. This was the total energy, and plus G capital M small letter m upon 2r. This is the energy that we need to provide to take that particular satellite from the gravitational pull. Alright, exactly, you can see the same. The next is escape velocity. Escape velocity is the same thing only. Fine. So here the concept is the same. Here we discussed about the binding energy. Alright, and what is binding energy? It is G capital M small letter m by 2r. Now let us consider a body kept on the surface of the earth. Okay, it's at state of rest. Now this particular body is going to have its total energy as G capital M small letter m upon capital R. There it was for satellite, and here I am considering it for a mass kept on the surface of the earth. Now this is the energy possessed by the body. I am just telling about the magnitude only. Negative sign means it is attractive force. That is the significance. Now if I want to take this body, or if I want to throw this body out of the gravitational field, so definitely I need to provide this much amount of energy to the body, and definitely I will be going to give that energy in the form of kinetic energy. And that kinetic energy value I can mark it as half of m into ve square, because finally this is going to escape out of the gravitational field. So the speed that I am going to give, I'm going to mark it as what? Escape speed or escape velocity. So this will cancel each other. So now this particular term is going to be v equal root of G capital M into 2 upon capital R. And we all know that G capital M upon R square, that is what? Small letter g. That means if I multiply this with capital R and small letter r, so definitely this is going to be what? 2gr. Exactly, you can see the same relation here. Fine. Now if the mass is written in terms of density, you can have the expression in this way, and this is the another modified version of the same relation. That's all. Alright, and the next one is weightlessness. So Weight is definitely being measured by a weighing machine, and weighing machine is always measuring the reaction force. Like for example, if I have a platform based weighing machine, there the reading on the display is based on the normal reaction that experienced by this flow. So if a machine is showing 0 reading, that means it is not experiencing a normal reaction. So if the normal reaction is increasing, the reading will be increasing. That means the machine will say that the weight of the body is increasing. And if it is not at all experiencing any normal reaction, then the machine will say that it is feeling like, as per the machine, the body is not having any weight. That is the basic logic. Please try to understand that. So if we can create any situation where the normal reaction is 0, all those cases is going to be treated as weightless condition. Which all are they? First one, free fall. We take this machine to the lift, drop that lift. If air resistance is ignored, this lift is free fall. In that condition, what? Normal reaction is going to be 0. So the body is going to be treated as a weightless body. Now if we take a spacecraft, okay, there let me consider a weighing machine there, something similar to this. Now there, if this particular entire setup is taken to an orbit, this entire cabin is experiencing acceleration due to gravity, and this lift, I mean the mass kept inside, I mean the weighing machine, that is also experiencing the same gravitational pull. The man standing there, he is also experiencing the same thing. Fine. So what will happen? There is no reaction between the man, because if the man is feeling greater pull, then only the possibility of normal reaction is there. Otherwise, normal reaction will not be there. So if normal reaction is not there, that means again what? Weightless condition. Okay. Now at the center of the earth, acceleration due to gravity is 0. So there is no pull. Fine. So at that case also what? Normal reaction is not going to be there. So weightless condition, definitely it will be there. And the last one is when a body is lying in a free falling lift. Exactly, I said that in the beginning, isn't it? So these are the cases where weightless condition is applicable. Fine. I hope you understood it very well. That was all from my end for these 3 chapters. We will meet you soon with another detailed discussion of another set of chapters. Till then, bye bye and take care.